Okay. Right. Okay. So, gosh. Right. Okay. So today we'll be talking about the second part of reductions, right? Okay. So, just a general reminder as always, right? What does it mean for a problem A to reduce problem B, right? So again, you have an instance of problem A, you have a superpower to solve any instance of problem B. Then, since you don't know how to solve A, but you know how to solve any problem of B, you convert an instance of A to an equivalent instance of B, solve it in B's world, and bring it back to its world. Okay. Right. So yeah, computational complexity theory. Before we begin, let's understand the difference between certificate instance and what does it mean to verify a certificate, right? Okay, understand easily by this example. So the problem is given a graph. Is there a path of cost at most k? Okay, so what's an instance? Okay, instance we talked about before. Instance is the input to the problem. So in this case, what are the inputs? The inputs are the graph, right? Because you're supposed to get the graph, the 2 points, the 2 nodes, and the budget, right? The budget, right? So those are the 3 inputs, right? Right. So we want to find is there a path of cost at most k? So you can see that it's a decision version, right, of the problem, right? Okay. So what's a certificate, right? So that's the instance. The certificate is something that claims to be the solution to the problem, right? So for example, the following certificate, this claims to be the solution, right? This can be a solution. Someone comes to you and say, okay, my solution to this problem is this, and he gives it to you. Example, right? So that's certificate. So until this one, does everyone understand? Okay. Can this be a certificate? Now, the path cost of that one is 2 plus 3 plus 4 is 9. Okay, so 9. So, by the way, the budget for this question, I put 10. Okay, so we want from 0.6 and 0.4, between 0.6 and 0.4, and the budget is 10. So, the weight of this path is 9. Okay, how about this certificate? This certificate is 2 plus 3, 2 plus 1 is 3, 3 plus 4 is 7, 7 plus 3 is 10, 10 plus 4 is 14. So, is this certificate or not? Yes, Aditya, is this certificate or not? Shahain. No. I mean, no to no. It is a certificate, except the fact that it's a no instance of the set, no instance of the problem. Okay, so please don't try to confuse yourself, right? Certificate need not be the yes answer or no. It need not be the yes answer always. Certificate can be something that someone proposes, right? Because by the definition, right, certificate is something that claims to be a solution. So it can be yes or it can be no. So this is also certificate. This is also certificate. This is a yes certificate. This is a no certificate. Okay, so please don't confuse yourselves. Okay, right? Right. So yeah, second one is also certificate. It's just that even though it claimed to be the solution to the problem, it is wrong. Yeah. Okay. So what does it mean to verify a certificate? So to verify a certificate in this example, you need to sum up the weight of all the edges on the path given to you by the certificate and check if the total comes is at most k. So to verify, just sum the edges and see with at most k. Right? To verify the certificate to that problem. Okay. Right. What does it mean to efficiently verify a certificate? Okay. So to efficiently verify a certificate means to verify a certificate in the time that's polynomial in the size of the input. Okay. So you verify that the path cost is at most k in time that's polynomial to the size of the input. Okay. So we learn what is a certificate, how to verify a certificate, and how to verify a certificate efficiently. Okay. Yeah. Right. Good. Another example, Sudoku. Problem is, I got this from Gemini, but whatever. If you want, I mean, it helps you, I guess. So this is Sudoku. The problem is, okay. The problem is, does this Sudoku grid have a valid solution? That's the decision problem, right? The proposed solution or witness, right, which is a certificate, is some completed Sudoku grid, right? We don't know if it's valid or not. Some certificate to the problem, some solutions, something that claims to be a solution. Verification, you check if the completed grid follows one Sudoku groups. That's the verification. Okay. Right? So that's the difference between problem, instance of the problem. So the problem is Sudoku. The instance is a certain partly added numbers here and there. That's the instance of the problem, right? And then the solution, proposed solution is verificate. The certificate is someone solved the grid. He says it's correct. Let's check it. That's verification. Okay, right. So class problems. P instead of all problems that can be solved in polynomial time. These are the problems that you usually deal with. Okay. Yeah. Okay. And yeah, NP. NP is a class of problems that have efficient verifiers for their certificates. Okay. That means if someone gives you a problem for an NP problem, you can verify that certificate in polynomial time. Okay. Okay. Yeah. So that P is solvable in polynomial time. NP is verifiable in polynomial time. Yeah. Yeah. So in this case, P is subset of NP because if someone gives you a P problem, and then if you want to prove that it's in NP, then you must be able to verify in polynomial time, right? But since you already can solve in polynomial time, do you need a certificate? No. You can just solve the problem and see whether it's true or false. Okay, Aditya, Chen, Joe, right? So that's why P is in NP because you really do not need to any certificate check. You can just solve the problem because you can anyway solve it in polynomial time, right? P problem. Okay, good. Yes, Jonah, is it okay until now? Yeah. NP hard, right? So please pay close attention to these two class of problems. Okay, NP hard means okay. So a problem is NP hard if all the problems in NP reduce to X. So whatever problem, like you can close your eyes and choose a problem in NP. You can always reduce this problem X if it's NP hard. That's the definition of NP hard. Right? A problem X is NP hard if all the problems in NP reduce to X. Okay. Okay. Yeah. So crucially, X can be inside NP or outside NP. Okay. I did not say whether X can be inside NP or outside NP. Okay. NP hard means all the problems in NP reduces to this X problem X. I did not say that X need to be inside NP or outside NP. I did not say that yet. Okay. NP hard means the property that all problems in NP reduce to this problem. Okay. Right. Yes. Okay. Okay, so practically, because we cannot reduce every NP problem to X because it takes too long, okay, right? We just reduce a non-NP hard problem to X. Okay, so then by transitivity, because we proved that this problem that we are going to reduce from already is NP hardware. That was NP hard because all problems in NP reduce to that problem, right? And by transitivity, you can reduce all the problems in NP to that problem, and that specific problem also reduces to X. So by transitivity, every problem in NP reduces to X. Okay, Shona? Shall we? Right. So, yes. So in this problem, by transitivity, you have all actually reduce every single problem in NP to X. Right. So is this hardest class of problems? It says NP hard. No. The hardest class of problems is when X is also in NP. In addition to being NP hard, X is also in NP. And those class of problems are known as NP complete. Okay. So to be NP complete, you have to have NP hardness. In addition to NP hardness, you also must be verifiable in polynomial time. Okay. So NP hardness means everything in NP can reduce to X, but X can be inside or outside. NP complete means in addition to being NP hard, you must be in NP. Okay.
I just explain that NP hardness.
Because you need to be able to verify in polynomial time the solution. It's an additional condition. Okay. Right. So my question to you is, you learned about 3 set, right? Okay. So is the problem 3 unset in NP? Okay. 3 unset. 3 unset means whether you can say for sure that this 3 set formula is unsatisfiable. 3 set means you can say that this formula is satisfiable. Okay. So 3 unset means you can prove for sure that this 3 set formula is unsatisfiable. Is this in NP or not? You can just you should be able to quickly say whether this is in NP or not. Why?
Because you cannot verify polynomial.
Yes. You cannot verify polynomial time, right? If you want to prove that, okay, so here's the deal, right? 3 unset means you want to prove that this 3 set clause has no solution, right? Okay. So to do that, your certificate itself must be exponential, right? Your certificate must enumerate every single possible assignment to variables, right? Because you're trying to prove that this is unsatisfiable. So you have to enumerate every single one and show that it's actually unsatisfiable. Whereas for 3 set, you can just provide one to prove that it is satisfiable, right? One assignment, right? But for whereas 3 set, you have to prove all sorts of true to the n many assignments to prove that it's unsatisfiable, right? Okay, Shahain? Aaron? Okay, Chen? Yeah. So your certificate itself is exponential. If your certificate is it's itself exponential, then how can you verify in polynomial? Because you need to at least check each of the certificates at each of the elements of the certificate at least once, right? So your verification is itself is exponential. 3 set is not in NP. So this is basically NP complete. So it's in NP and everything reduces to X. Yeah, Jova. You have yeah, this one was taken from Prof. Stephen Halim's slides last year. So. Okay, so question number 1. Which of the following implies P equals NP? Who's present today? Yeah, you know, yeah. Which of the following implies P equals NP? A. There is a problem in P that's also NP complete.
Yeah,
Sorry.
it's true. Here it is. I mean, it means that, this statement, it means that, it means that NP complete should be solved when.
Okay, if there is a problem in P that's also NP complete, then NP complete means it's NP hard also, right? Then what does it mean to be NP hard? Everything reduces to it, right? In NP.
Wait, sorry, again.
So for if a problem that is in P is also NP complete, that means it's NP hard, right?
Yeah.
So then if it's NP hard, then every problem in NP reduces to it, right?
Yes.
So then every problem reduces to polynomially solvable problem, right?
Mm-hmm.
So then everything is polynomially solvable, right?
Yeah.
So then NP is P, right?
Yeah.
Yeah.
But that's not.
Yeah. I mean, no, we really do not know the P is
Yeah.
NP. If you can say for sure, you can win $1 million.
Yeah.
Right. So does everyone understand this? Okay. Right. Good. Yeah, because the last part is a bit heavy. That I'm quickly rushing through the easy stuff. Right. Okay. There's a problem in okay. I just show the answer. There's a problem in P that is also in NP. Okay. What I mean is this, right? This is false in the sense that this does not prove P equals NP. Okay. This does not mean this statement is false. I mean, surely there's a problem in P that's also in NP, right? Because P is a subset of NP, right? And we know that P is non-NP, right? Okay, so there is a problem in P that is also in NP, right? Okay. So when I say false, I mean this does not prove P equals NP, okay? Right, okay. Okay, there's a problem in NP that's also NP hard. Yes.
No,
Why?
because if it's in NP and NP hard, it's NP complete.
Yes. So does that prove P equals NP or not?
No, existence of a complete doesn't prove P equals NP.
Yeah. Okay, so in this case, like false in saying it does not prove NP equals NP because what you're saying is essentially there is NP complete problem, which does not prove P equals NP, right? Because we already know that there are NP complete problems and P. Yeah. Okay. So this does not prove that P equals NP. Okay. So this is the one that proves P equals NP. So in the future, if you want to prove P equals NP, just try this. Okay. Yeah. Right. Question number 2. Right. Okay. Okay. So this question, right? When I was doing this, is the only question that I was not able to do out of all the tutorials last sem. Okay. So, but I was really close to solving this. But yeah, I spent too much time wasting time on this, so I just okay. Right. Yeah, I was really close, but I had the correct idea, but yeah. Right, so let's begin. Prove that subset sums NP. By the way, I thought everyone has read the problem, right? Because I don't want to waste time, right? Everyone has read the problem, right? Okay, the subset sum. You want to subset that sums to this term, right? Okay, so let's begin. Prove that subset sum is in NP. So what should you do to prove that it is in NP? Yes, sir. Actually, who's present today? Churnya or Aditya? Shahain, right? Okay, yeah, Shahain. What do you need to do to prove a problem is in NP?
Just take a certificate and then show that it's
Yes. So in this case, what's the certificate?
subset.
Yes.
Get.
So you need to sum up all the ways, right? Okay. Yeah. So given a subset, given a certificate I, you just need to add all the elements in the certificate, right? and then you check whether it's equal to W. Okay, that's subset sum. Okay, so that can be done in linear time, right? Okay, easy stuff. So you yeah, okay. So I need to say this, right? So you only need to ensure that the verifier runs in polynomial time, right? Even if you cannot figure out this linear time thing, even if you can solve it in O of n to the 5 time, right? Which is suboptimal, right? Still you have proven that this problem is in NP because you verified it polynomial time, right? Okay, so your verification does not need to be absolutely the fastest. Okay, in the exam, right? You don't need to think too hard. Okay, you need to just provide some polynomial verification, even though it's slow, as long as it's polynomial. Okay, do not try to make life hard for you. Okay? So it does not have to be the fastest possible. So don't leave this question blank in the exam. Okay, just write. I mean, it's pretty easy to get this actually in the exam. Okay, so please don't leave it blank. Okay, right. So prove that subset sum is an NP hard by showing 3 set reduces to subset sum. Okay. Right, okay, so you want to prove that 3 set will reduce to subset sum. Now that means given arbitrary instance of 3 set, you need to convert to equivalent instances of subset sum. So that using the superpower to solve subset sum, you can solve 3 set. Zero. Right. So let's begin. Yeah, so what's goal? What's our goal? Basically this thing, right? This thing, right? So you have an instance of 3 set, you have this instance of subset sum, you don't know how to solve subset sum. Sorry. You know how to solve subset sum, but you don't know how to solve 3 set. So you reduce from 3 set to subset sum and solve in the subset sum world. Okay. So to do this, you need to create equivalent instances, right? Okay. That are representative of the actual 3 set instance, right? Because otherwise you cannot get any value. Okay. Right. So find transformation from alpha of 3 set to instance of beta of subset sum such that alpha is just plus beta is just and beta is just plus alpha is just. And also the transformation is polynomial. Right, okay. So yeah, so consider a 3 set formula with n variables x1, x2 until xn and m clauses c1, c2 until cn. Okay, so variables are not literals. Okay, so a literal can be x1 bar. Variable means just the atomic thing x1, x2 until xn. Okay, literals can be the negation, whatever. Okay, right. So variables are these and clauses are c1, c2 until cn. Okay, so we need to define an input to the subset sum problem somehow. Because we're trying to reduce, right, from 3 set to subset sum. I.e., you need to define numbers wi, right? That's it set, right? And the target sum w that is equivalent to this 3 set problem. Somehow there must be an equivalence, right? Because you're trying to solve 3 set using subset sum, right? So you must create a related input, right? You cannot create some arbitrary input and hope that it works, right? It will not work. One of these two will fail if you create arbitrary stuff, right? Okay, so you need to create equivalent instance, right? Right. So recall what is xi. Okay, what is xi? Yes, Chen. What are xi? Variable, right? Yeah. Okay. So okay, let's start. Start by having two numbers ai and bi associated to each variable. Where including ai means setting xi to true, and including bi means setting xi to false. So these ai and bi live in the subset sum world. Okay. Okay. So including ai means setting xi to true, and including bi means setting xi to false. Okay, so recall AI and BI live in the subset number. Okay. So, alright. Okay, so now, okay, so we have AI and BI for each variable, right? Okay. So to do this for all I in 1, 2, 3 until n, so for all variables, right? You define these two numbers. Okay. So AI, you define AI as follows and BI as follows, right? Okay. So don't be afraid of this thing, right? What this says is ai is equal to 10 to the m plus I. So I is so this I belongs to uniquely to every single variable, right? So x1 has I equals 1, x5 has I equals 5, right? 10 to the m plus I. So what is m? What is m? Okay, so you m is the number of clauses, right? Okay, so please keep in mind, right? M is the number of variables, m is the number of clauses. So you have clauses like 3 set clauses. Okay. Okay, so please keep those in mind because otherwise you get lost. Okay, so ai is 10 to the m plus I plus this sum. Okay, let's talk about it later. And bi is 10 to the m plus I plus sum. Okay, right. Okay, so let's talk about this part now. Okay, so you're summing 10 to the j where 10 to the j where j comes from, okay, so you're summing over all j such that the clause Cj contains xi. Okay, so this needs some time to process, right? Okay, so ai, you for each variable you define ai and bi, right? Take this sum, right? You're summing, you're going to enumerating over all j's, right? All clauses, you go through all clauses, like this clause 1, clause 2, clause 3, clause and if that clause contains xi, you raise 10 to the that clause number and add it. Okay, so for each variable xi, you run over all the clauses, right? And if you discover that clause has xi in it, then you raise 10 to the clause id and add it as ai. Okay, Aaron?
I think it's something. Yeah.
Okay, so basically for every single variable, you define ai and bi, right? So ai, to define ai, you run over every single clause, right? In every single clause, you check whether xi is present.
Basically, check that xi is present.
In a clause. Okay, so for example, these are clauses, right? So for example, let's say I'm running over this, right? And I see x1 is present, right? So and this is clause 1. So then to this sum, I add 10 to the 1 because it's clause number 1. And okay, so I added 10 to the 1 and I also come to this one. I see x1 is also present in clause number 2. So add 10 to the 2 also. Okay, Shahain. Tuna. Okay, right. Okay, good. Okay, so that's like half of the part done. Okay, so so for xi you define bi also. For this you go over every single clause, and if it contains a negation, you raise 10 to the I and add it to your sum. So for example, right? Let's say I'm defining b2, right? So for b2, I need to loop over every single clause and see whether the negation of x2 is there. So in this clause, I can see x2 negation. So I add 10 to the 1 to bi. Then I go to this one. I don't see a negation of x2, so I don't add anything. Okay? Okay. Check. No, I sure you understand this. Okay. Okay, Joshua.
Yeah, I need to catch up.
Okay. Okay, slowly. I thought of putting this in the group define, but I didn't. Yeah. On this 1 second. Okay. Let me just follow around. Okay. Right. Okay. Right. For example, if 3 instance was this thing, right? So for x1, you define a1 and b1. So to x1, 10 to the m plus 1. M is the number of clauses. How many clauses? 2. 2 plus 1. 10 to the 2 plus 1 plus. You can see that for a1, right? You can see x1 is present in the first clause, x1 is present in the second clause. You add 10 to the 1 plus 10 to the 2. Okay. So for x1, you define b1. b1 means 10 to the 2 plus 1. That's same for a1 and b2. A1 and b1 plus 0. Because you can never find x1, the negation of x1 in any clause, right? Right? Jonah. Okay, so you don't have anything, right? So for x2, you define a2 and b2. a2, 10 to the 2 plus 2, because 2 is the number of clauses and 2 is the index of the variable. Plus 10 to the 2, because you can find x2 in the second clause. Okay? And then similarly, x2 for x2, you define b2, 10 to the 2 plus 2 plus 10 to the 1, because in the first clause, you can find the negation of x2. Okay? Okay. Right, good. So x3 is also defined very similarly. Now, consider a yes instance of 3 set and the corresponding subset of the numbers so far, containing ai if x equals 2 and containing bi if x equals false. So we have a 3 set instance, and in this 3 set instance, you're given some assignments, right? So x1 is true, x2 is false, something, right? So if x1 is true, you select a1 in your substance sum problem. If x2 is false, you select b2 in the substance sum problem. If x3 is true, you select a3 in the substance sum problem. And then you sum all the a's and b's together. I'm talking about that sum. Okay. Okay. So keep that in mind, right? I claim that the resulting sum is of the following form. The first one is that it has a 1 in the leading n digits. Okay, so what's n? Yeah, what's n? Now I need to keep on reminding you. What's n?
The number of
variables.
Yes, correct. Number of variables, right? Okay. Corresponding. corresponding to 10 to the n plus I for I equals 1, 2, 3 until n. Okay, so let's see why, right? Now, for every single variable, if it's true, we include AI. If it's false, we include BI, right? So in that case, we include for every single variable, we include either AI or BI, right? So in that case, by the definition of n plus I, when I runs from 1, 2, 3, 4 until n, that means we actually cover the first n digits, right? Because for every single, okay, so for every single digit starting from the left of the number, right? For every single index, either that one comes from this one or that one, right? Because we are adding either AI or BI, right? Okay. Okay. So the form is like this, right? So currently the sum looks like n ones and rest of the number. Okay. So this one corresponds to the first variable x1, x2, x3, x4, x5, x until xn. So for x1, right, you included either AI or BI, right? But AI or BI has this one, right? By the definition, right? AI or BI. So imagine that you forget about this 10 to the m. This is like a padding of zeros, right? But for every single AI or BI, you add either this or that, right? But this or that corresponds to these unique bits. So this unique bit came from x1. This unique bit came from x2. This unique bit came from x3, and this unique bit came from xn. Okay, Aaron.
So the rest of the number behind is due to the n.
Due to the m. Okay. So let me clarify this again, right? So we have 10 to the m plus I, right? So I goes from 1 to n, right? So the largest, so then you have n digits in the front, and then you have m digits at the end. Okay, there's a small tweak, but okay. So 10 to the m is the digits at the end, and these 10 to the i's are the digits at the front. Okay, just keep that in mind. It helps you to understand a bit. So 10 to the m is just a padding of zeros. Okay. Okay. So yeah, Aaron, you're correct in the sense that these are m digits. There's a small condition to that, and these are the leading n digits. Okay, you're adding 10 to the m plus i's, right? Okay, so you have n many ones and the rest of the number, but we can guarantee say that the first n have to be 1, 1, 1, 1. Is it okay? Juni? Okay, I should.
To a certain extent.
Okay, I know it's hard to understand, but okay. So do you understand that for each single variable xi, you add either AI or BI, and AI or BI has a 1 in that position because of this 10 to the m plus I. Okay, so one thing, right? You're running j over cj's, right? So what's the largest j that can come here? M. This one, what's the smallest 10 to the power that can come here? 10 to the no 10 to the m plus 1, right? So these 10 to the m plus 1s are disjoint from these 10 to the j's. Okay, because the largest j that can happen is m, because the largest clause number is m, right? Then this is 10 to the m plus something, and these i's are at least 1. So this power is at least m plus 1, 10 to the m plus 1. Okay, so these 10 to the m plus 1s are disjoint from these powers of 10s. Okay, so these powers of 10s can add up to m digits at the end. These 10 to the m plus i's add up to the n digits at the front, because I can go from 1 to n. Juni, is that okay now? No, I sure is it okay?
You know what I mean? Like I get the math side.
Okay.
I can't fully piece things together.
Okay. Let's get to that report in a bit, right? Okay, so you have n1s and then m many digits. Let's put that as a asterisk, but your idea is correct. So you have n1s and m whatever numbers at the end. Okay, right. So next thing is it must have a 1, 2, or 3 in the next m digits. Okay, so you have n number n1s and you have m digits at the end, right? So I claim that all those m digits must have 1, 2, or 3. Why? Because the digit of 10 to the j is exactly equal to the number of true literals in clause J. Okay, let's see why, right? For example, right, you have this number, right? You have n1s and you have m whatever numbers, right? I claim all those numbers are 1, 2, or 3. So you look at this jth bit, just I randomly choose some jth bit, right? So this jth bit corresponds to the jth clause. Okay. Okay. So these corresponds to actually variables. This corresponds to clauses. Okay. So this corresponds to jth clause. Okay. Now, okay. So now say for example that jth clause is x7 or x9 bar or x4 bar. Okay. Now, then okay. So then understand this, right? So then only a7, b9, and b4 have a 1 in the jth position. Only those three numbers have 1 in that position. No other number on earth has that number. Not every number on earth, but out of all the numbers that we created, no other number has a 1 in that position. Only A7 corresponding to X7 and B9 corresponding to X9 bar and B4 corresponding to X4 bar have a 1 in the jth position. Because these are jth clause, right? Shall we? Arjuna? Arjuna?
Yeah.
Okay. Right? Only these three numbers have 1 in the position. You can say for absolute sure. Now, no other number has a 1 in that position. Okay. By the way, we define AI and BI, right? Okay. So my question to you is, why doesn't B7 have a 1 in the jth position? So I said A7 has a 1 in the position, but why doesn't B7 have a 1 in that position? Yeah, can say.
This is 0.
Sorry.
0 and back, right? Like you define the B7.
Yes, B7 as. Yeah. Okay. So yeah. Okay. In that example, yes, it's 0 at the back. Well, but why is it 0? Okay. So that example is different from this one. But logically, can you say why B7 will not have 1 in that position, in the jth position?
It's already in the B, I mean X7
Yes.
location.
Yes. So for B7 to contain a 1, that means X7 bar must be present in this clause, right? So do you find X7 bar in this clause? No. So the only numbers that can actually have 1s are A7 because X7 is in this clause. You can find B9 because X9 bar is in this clause, and B4 because X4 bar is in this clause. Okay. Right. So okay. Now the next thing is, because 3 set is satisfied, okay, therefore at least one literal among these are, and this must be true, right? These are definitely 3 set, yeah. At least one of these must be true, right? For this literal to be true. Yeah. Okay. So that means either X7 is true or X9 bar is true, X9 bar, right? Or X4 bar is true. That means if X7 is true, you are including A7. If X9 bar means X9 is true, X9 is false, that means you include B9. If X4 bar is true, then X4 is false, that means you include B4. Then that means you are including at least one of these numbers that contain a bit in the jth position, right? So then in the jth position in this final sum, the number must be at least 1, right? Okay, so because of the 3 set is satisfied, you have to include either A7 or B9 or B4 by the definition, right? Because if Xi is true, we include AI. If Xi is false, we include Bi. So by this definition, right? If X7 is true, we include A7. If X9 is true, then X9 bar is true, then X9 is false. That means you include B9. Because X9 is false, you include B9. If X4 bar is true, then X4 is false, that means you include B4. So in that case, you're including one of these numbers, right? You're including at least one of these numbers, and at least one of these numbers have, all three of these numbers have 1 in the jth position. So if you at least one of these, then surely the jth position must be at least 1. Okay. Shall we? Okay, right, good. So in the other extreme, it must be at most 3. Why? Why should it be at most 3? Yeah, because only 3 numbers have 1 in the jth position, right? So even if you add all the numbers in your new set, you will not get greater than 3. Okay? Shall we? Yeah, error? Okay, right, good. Yeah, okay. Yeah, so currently the sum looks like this, right? You have n ones and m digits, and all these m digits are either 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay? Right. But there is a small tweak in that there is 0 at the end. Why? Because in these sums, right, you're powering 10 to the positive numbers, right? You don't power 10 to the 0, right? So when you add there is no digit in the 0 position. So there is a 0 at the end. Okay? Right? Because all of these 10 to the anything is at least 1. So okay, you don't add a unit position. Okay? Right? So there is a 0 at the end. Okay? Right. So you have 0 at the end. Okay? So this number is n plus m plus 1 bits. N at the front corresponds to variables, m corresponds to clauses, and there's a 0 at the end. Okay? Is that clear? Right, good. Next point. Right. So to turn this into an answerable subset sum problem, we need to add a few more numbers, right? After all, right, we did not still define the target W, right? We still don't define W. So we need to define that one also. We define the weights, that for sure. But we need to define the W also, the target, right? So we define W in the following way. So W as you sum all I from 1 to n, 10 to the m plus I plus 3 times 10 to the j equals 1 to m. This is not confusing, okay? W looks like this. This is W. Okay, so this is W, those are the weights. So these are the weights, this is W. Can you see it's almost the same thing, except instead of 1, 2, 3, we have 3, 3, 3, 3, 3. Okay? Clear so far? Okay, Junli? Yeah. Right, so you should see the trickery at play by now. What we're trying to do. We are forcing these numbers, I mean, these threes, okay, I mean, it shouldn't be that obvious, but you should see where we are going with this, okay, by defining W as follows, right? Okay. We also need to add these numbers, Cj and Dj to our sum. We will talk about why we add Cj and Dj. In addition to Aj's and Bj's, we also have Cj's and Bj's, right? For j equals 1 to m. Okay, so be careful, right? Ai and Bi correspond to variables. Those range from 1 to n. Cj's and Dj's range from 1 to m. Okay, so please be careful, right? These correspond to adding numbers. These correspond to adding numbers in these positions, this last m position, right? Because j equals 1 to m. So Cj's and Dj's correspond to the last m, right? Ai's and Bi's, I mean, also correspond to, they also add things in the last m, but they mainly correspond to the first n digits. Okay. Okay, Junli? Yeah. So please don't confuse. Okay, so at last the transformation is complete. So we're done. So we define A's and B's and C's and D's and W. Okay, for our new problem. Okay. So we want to show the transformation is correct. Like how do you show a transformation is correct? We need to prove yes instead of this implies the yes of that, and the yes of that implies yes of this. Okay, so consider a yes instead of 3 set. So for every variable xi, because you have 3 set, because 3 set is true, then we have satisfying assignment, right? So every single variable xi, if xi was true, you include ai. If xi was false, you include bi. Okay, right. Easy to see by the claim above that this gets the leading and it is correct. Yeah, I remember.
So for each variable, you just select either
Yes.
Yeah.
So for each variable, you select either ai or bi, right? So that means for every single bit in the first n positions, it's guaranteed that some variable will contribute 1 to that number. Also specifically, to this one, x1 will contribute. To this one, x2 will contribute. To this one, x3 will contribute. To this one, x4 will contribute. To this one, xn will contribute. Okay, right, good. Because again, it's right. It's 10 to the m plus I. So this I is unique to a variable, right? Okay. Right? So only one variable will contribute to one of the positions in the first n. Okay, so be careful. Okay, right. So to make the remaining digits, but what are the remaining digits? The digits at the end, right? We may need to add Cj or both Cj and Dj, depending on if the digit is 3, 2, or 1. Okay. Okay. Now because you're adding AJs and AIs and BIs, right? I said that by the claim, right? These numbers at the end are either 1, 2, or 3, 1, 2, 3, 1, 2, 3, right? But we want the target to be 3, 3, 3, 3, 3. So if you sum the MDs at the end, if you sum those, collapse them, and then you compare with this part, right? Either that sum can contain 1 or 2 or 3, 1 or 2 or 3, 1, 2 or 3, right? And because when you add these numbers, right? When you add these numbers together, you focus on the last m digits, right? Because each digit is 1, 2, or 3. Then after you sum all those numbers, then the sum at each digit can be 1, 2, or 3, right? Okay, but at most 3, right? We proved that before, right? Okay, so then these positions after you add them can be 1, 2, or 3. This can be 1, 2, 3, 1, 2, 3, 1, 2, 3. So, but we need 3, right? So therefore, we define these CJs and DJs, right? You strategically use some CJs and DJs to make the sum because we define these for 1 to m. We define those for this last digits. So if the individual units actually sum to less than 3, you strategically select some CJs and DJs and get the sum to 3. Okay, Junior.
So what if it doesn't sum to 3, it's like only 1? So
Yes.
then what the CJ or DJ, what's the number of CJ and DJ?
So suppose that this does not sum to 1.
Yeah.
It sums to that's a sum to 3. It sums to 1, let's say.
Yeah.
Then this corresponds 10 to the m, right?
Yeah.
Because this is the m clause 10 to the m.
Yeah.
So we define for j equals 1 to m, right? So we have the 10 to the m in CJ and DJ, right?
Yeah.
So you select both of them and then you add it to the sum. Then you automatically get to 3, right?
Oh, okay, yeah.
So
Okay.
that's what I mean by adding, getting the CJs and DJs into action. Yeah.
Okay. Okay, maybe go because I still don't see. I mean, then how do you know what?
Okay, maybe I'm not there yet, but until this point, is it okay?
Yeah.
Okay. Until this point is okay, right, everyone?
So the constraint is like it just has to be non-zero, but you're adding that because of the constraint of the
Yes, because I add the constraint that all of the last m must be a 3, 3, 3, 3, right? But when I add the AIs and BIs in my set sum problem, we prove that those last m digits can be either 1, 2, or 3. When you sum them together, also it's at least 1 or at most 3, right? We prove that, right? We prove that here. We prove that here, right? After you sum those numbers in the last m digits, the unit can be either 1, 2, or 3. But we want the unit number to be exactly equal to 3, right?
because of the subset sum.
Because we define W in this way. Okay? So therefore, we need to add these CJs and DJs to compensate if it does not add up to 3.
Right. So if one of the M digit is like, okay, so let's say it's 2, then we just add one of the CJ or DJ.
One of the positions is 2.
Yeah.
Yes,
so just add CJ or DJ.
CJ or DJ.
Not both, right?
No.
Both were existing.
Yeah, because I think I said it before.
Yeah. Okay.
I said we may need to add CJ or both CJ.
Yeah.
Okay. So if it's 2, then you need to add CJ or DJ. If it's 1, then you need to add both of CJ and DJ. Okay. Right. Good. So in this way, if 3 set was yes, if 3 set was yes, then subsum is yes, right? Because we add up everything to W. Okay, Jim? Clear? Okay. Right. So there's one more step. Now we want to prove that in this crazily developed subset sum world with all the AIs and BIs, we want to prove that if the subset sum is yes, then actually 3 set is also yes. Okay, so let's start. Yeah, this is also actually pretty easy. It's not really hard. Okay. So first note that for any digit 10 to the k, there are at most 5 numbers with a 1 in that digit. in this new sum, in this new subsystem problem, right? We define. So we prove that either that age, for example, right? For this literal, right? We know that A7 has a 1 in that position, B9 has a 1 in that position, B4 has 1 in that position. So three numbers already have 1 in that position, right? In addition to them, we know that the CJ and DJ also has a 1 in that position, right? Yeah, right. So therefore, we have five, at most 5 numbers in that with 1 in that jth position. Okay, right. Right. Okay. Why did I say at most 5 numbers? Doesn't it seem exactly to 5 numbers? I mean, AJ and A7, B9 and B4, and CJ and DJ for that position, right? So isn't it exactly 5? Yes, it is exactly 5 for the last m digits, right? But for the first m digits, it's at most 5. Right? Because so why did I say that? For every digit 10 to the k, there are at most 5 numbers with a 1 in that position. But we just prove that 3 numbers definitely have to have a 1 in that position. And we also have that CJ and DJ, right? So there are 3 plus 2 is 5, right? We just prove definitely there must be 5. But why do I say at most 5 numbers with the 1 in that position? Because we don't consider the first n, right? First 10 digits, right? For the last 10 digits, there are exactly 5 now. 5 ones, if you take all the numbers, right? But for the first n, for the first n digits, right? If k is greater than m, there are at most 2 numbers with a with a 1 in that position. So why? So if k is at most m, so k is actually the normal parts, right? At the end, right? So for these ones, yes, we know that there are exactly 5 numbers with a 1 in this position, 1 in this position, 1 in this position. But for these first n digits, there are at most 2 numbers with a 1 in that position. Actually exactly 2. Why?
Are you trying to say because you can have both the the literal true and false value in the CNF. So
Yes, that's true. But what I'm trying to say is that for every single one of these positions, there's exactly 2 numbers with a 1 in that position. So for this one, only A and Bn has 1 in the position, right? For this person, only A n minus 1 and Bn minus 1 has a 1 in the position, right? For this one, only A1 and B1 has a 1 in the position. CJ and DJ don't have 1 in the position. Because CJ and DJ correspond to these numbers, right? So only exactly 2 numbers will have 1 for the first n digit, for the first n bits. Okay? Right. Good. Is that clear? Aaron? Jen? No, it's just that.
piece, I understand pieces, or we can piece together now.
Okay. So my point is that the first n digits must have you can only find at most 2 numbers in your entire collection that sum up to that have a 1 in the position. But for every single number towards the end, the last m, you can find 5 numbers that have a 1 in the position. Okay, so namely those CJ, A7, B9 or B4 that we proved, for example, that answer, and also CJ and DJ. But for the first 10 digits, we only have AIs and BIs. We don't have CJs and DJs because CJs and DJs are only limited to the last 10 digits. Okay. So yeah. Now this one, right? With only 5 ones in any position, I think whatever subset of numbers will not cause a carryover. Because in every single position, you only have exactly one, at most 5 ones, right? In every single position, if you consider all the numbers. So even if you had all the numbers, it will not cause a carryover, right? Okay. Right. So we can only get the total of W by including the right number of ones in any big position. Because there are no carryovers, right? You don't need to be intelligent. You only need to get the number of bits correct at every single position. You don't need to consider carryovers and how the carryovers will affect, because there will be no carryover. Because there are at most 5 ones in any position. Okay, David? Right. Okay, right. So now how does W look like? You have n ones in the first 10 positions and 3 m's, sorry, n threes in the last 10 positions and 0 at the end, right? Okay. This means that we can never choose both AI and BI. Why can't we choose both AI and BI?
Maybe a 2.
Yes, because there will be a 2 here, right? In the first 10 digits, there will be 2, right? Because AI and BI both have 1 in that position. So if you choose AI and BI, then 1 plus 1 is 2, right? Then you will violate these. Consequently, also, you can never choose none of AI and BI. Why? Because then it will be 0 at the front end. Okay? Shall we? Achuna? Third one, we can only choose one of AI and BI. Okay, I mean, if these don't happen, then surely you can only choose one of them. Right? So can't you see that this aligns with true false? Right? The way we did that, we somehow made that any subset sum that adds up to W, we forced it to only contain either AI or BI, guaranteed. Okay, right? So that means the problem is actually solved now because yeah, you're done. Okay, so if AI is true, then set xi equals true, and if AI, if you choose BI out of AI or BI, right? Then you set xi equals false as in 3 set. Now this is assignment 2, 3 set, and then the only thing that you need to prove that this set is satisfying assignment. Okay. This actually automatically makes 3 set true because for every clause k, right? For every clause k, 1, 2, 3 until m, right? This corresponds to the kth bit, right? Kth bit from the this kth bit, one of these bits, right? They correspond to clauses, right? Okay, so to the kth bit, we chose some AI and BI that had the kth bit, right? Right? Okay, I mean because of this thing, right? Okay. Now for the kth bit, right, you need to select some numbers such that yes. Okay, I forgot to say something. Right. So I also want to prove that for each of these positions, right, when you add the specific AIs and BIs, the bit in that position must be at least 1. For this position, because if the bit was 0, then even if you add both CJs and DJs, can you get to 3? No. Then that means you should have for every single one of these bits, right? This one, this one, this one, this one, this one, this one. You should have chosen some AI that has this bit in it, right? Because if you never chose an AI or BI that had that one the bit in that position, then even if you add both CJs and DJs, then clearly you cannot get to 3, right? So that means for each one of these bit positions, you had some AI or BI that had 1 in that position. So what does that mean? For every single clause K, you had an AI or BI that had a bit in that 1 position, right? By the definition, then that means that clause had, for example, if you chose AI, then that clause had XI. If you chose BI, that clause had XI bar. Then you automatically set every single clause to true, right? Yeah, right. So then it's a 3 set, yes. Okay. I know it's a bit of a whirlwind too, but I hope you get the gist of what we're trying to do, right? We define W creatively so that we force only AIs or BIs to be selected, and depending on whether AI or BI is selected, we prove that yes instance of 3 set actually yes instance of subsum also actually corresponds to a yes instance of 3 set. So it's a bit, I know it's a bit weird why we do this, but this is the creative way to do this. Okay. Yeah, by actually juggling both parts of the first part of the W and the second part of W. That's the crucial thing you need to understand, that for every single one of these positions, you should have chosen an AI that corresponds to this one. You should have chosen some AJ that corresponds to this one. You should have chosen some AK that chooses this one. Because if you did not choose any AI or BI that had 1 bit in that position, because even if you add CJ or DJ, you can never get to 3. So the moment you add the AI or BI, you immediately set that false to true, that clause to true in your preset. So because you guarantee for every single clause, then every single clause is true. Yeah. So that's a pretty interesting problem. you will not get this kind of problems in the exam. I think, I hope. Yeah. Okay, so the next question, right? Before the next question, I got some stuff because the next question is actually pretty easy. Right. Yeah, you guys can share. For the KitKat, just take one. For Toblerone, you take two. Toblerone is locked. Okay. Yeah, okay. So the second question, right? It's actually pretty easy, but I don't think I have time to cover it now, guys. But yeah, this is actually pretty interesting. Okay, so what I'll do is I'll record a video and send it to you all. Because the second one is much easier than the first one. It's like this one is nothing. I solved it in like maybe 10-15 minutes. Yeah. I'll send a record video for this one. Yeah, I think because I don't want to drag on because otherwise Jalika will shout at me. Who is that? Jenkins. Yeah.
Just to confirm your career. So essentially what I try to do is one part ensure you choose only one no conflicting literals, and the second part you ensuring that each clause has a true.
Yes.
And then you add CI and B, CJ, DJ as like below value.
Yes.
To ensure that it's always true.
Yes. You add CJs and EJs to get the front part correct. The yes of reset to yes of Sadhisa. But for the reverse part, you don't use CJs.
Okay, then so you add all A, B, C, and D in the list, and then you choose the subset sum that corresponds to W. That's the
Yes.
okay.
Okay, guys, let's take a photo. Okay. Okay, I just ask someone else from outside to come at info. I just come to center.